All right, let's talk about one of the wildest, most mind-bending ideas in all of science. We're going to try and demystify something that sounds like pure science fiction, but might just be the truth about our universe. String theory.
So, what is the universe really made of? I mean, at the most fundamental level. For a long, long time, we thought the answer was simple. Tiny little dots, right? Indivisible particles. But what if that's wrong? What if there's a completely different answer? One that's way more elegant and way, way weirder.
Okay, so let's get right into it. The central idea of string theory is that deep down, everything is a string. This isn't just a small tweak to our understanding. It's a total rewrite of what we think the building blocks of reality actually are.
You know, for the longest time, we've pictured fundamental particles, like an electron, for example, as just these little teeny tiny zero-dimensional points, dots. But string theory comes along and says, whoa, hold on a minute. It says if you could zoom in like way, way closer than we ever have before, you'd see that electron isn't a dot at all. It's a tiny, one-dimensional, vibrating little filament of pure energy, a string. And here's the really beautiful part. This means that everything, and I mean everything, from the light hitting your screen to the atoms that make you up, is all made of the exact same stuff. The only difference is how that little string is vibrating. So if a string wiggles one way, we see an electron. If it wiggles another way, bam, it's a photon, a particle of light. It's kind of like a guitar string, right? The same string can play a C note or a G note or an F note just by vibrating differently. The universe, it turns out, might just be one big cosmic symphony. Now, these strings basically come in two flavors. You've got your open strings, which have two little endpoints, kind of like a piece of spaghetti. And then you have closed strings, which are complete loops, more like a rubber band. The cool thing is how they can interact. They can join together, they can split apart, and an open string can even join its ends together to become a closed loop. That little detail, it's going to turn out to be a really, really big deal later on. Just keep that in the back of your mind. So you might be thinking, okay, vibrating strings, that's a pretty weird idea. Why did we need it? Well, it's because modern physics has a giant gaping hole right in the middle of it. A tale of two physics, you might say. Okay, check this out. We have these two powerhouse theories that describe our universe, and they are both spectacularly good at what they do. On one side, you've got Einstein's general relativity. This is the boss of the big stuff. Planets, stars, galaxies, the smooth fabric of space-time. It's beautiful. On the other side, you've got quantum mechanics. This is the theory of the really small stuff. Atoms, particles, all the fuzzy, weird, probabilistic chaos of the subatomic world. The problem? They hate each other. They're totally incompatible. The rules of one completely contradict the rules of the other. And this isn't just some academic debate. This conflict becomes a full-blown crisis when you try to describe places where the very big meets the very small. Think about the center of a black hole, where a ton of mass is crushed into a tiny space, or the very first moment of the Big Bang. In these places, you need both theories to work together. And when you try to do that, the equations just break. They literally spit out nonsense, like infinity. The whole system just falls apart. So how do we fix this? How do we unite the universe? Well, this is where string theory comes onto the scene. And what's wild is that it offered this incredibly elegant solution almost by complete accident. See, the funny thing is, string theory wasn't invented to be a theory of everything. Not at all. Back in the late 60s, it was just this quirky idea to explain the strong nuclear force. You know, the stuff that holds the guts of an atom together. Gravity? Nobody was even thinking about gravity. But then, as scientists were playing around with the math, they found something, well, something they couldn't explain. A little piece of the theory that just didn't seem to fit. And they realized gravity wasn't something they had to cram into the theory. No, it was already there. It just popped out of the math, all on its own. It's not just a feature, it's a requirement. You literally can't have a consistent string theory without gravity being part of the deal. And here's how it works. Remember those closed-loop strings we mentioned earlier? Well, it turns out that one specific way that a closed string can vibrate, one particular note it can play, has the exact properties of a particle that physicists had been dreaming about for decades, the graviton. This is the hypothetical particle that carries the force of gravity. String theory didn't just suggest that the graviton could exist, it demanded it. It was baked right into the recipe from the very beginning. Okay, so string theory magically unites the two pillars of physics. It's perfect, right? Well, not so fast. Because to get this beautiful mathematical picture, you have to accept some, let's just say, mind-bending things about reality. We have to go beyond just strings and dimensions. Here's the first big one. The math of string theory simply does not work in the universe we think we live in, with 3 dimensions of space, up, down, left, right, forward, back. For the equations to make sense, the universe has to have more, like a lot more. Most versions of the theory need 9 or 10 spatial dimensions. So where are they? The idea is that they're curled up, compacted down so incredibly small that we just can't see them in our everyday lives. And the theory itself just kept getting deeper. It wasn't a static idea, it kept evolving. It started out as just one thing, then people found 5 different versions of it. But in the mid-90s, there was this huge breakthrough, and all those different versions were shown to be just different sides of the same coin, a bigger, more complete idea called M-theory. And M-theory didn't just have strings, it introduced these other objects called branes, short for membranes. You can think of them as these higher dimensional surfaces that exist within that 10-dimensional space. And remember our open strings, the ones with the endpoints? Well, it turns out their ends have to be stuck to these branes. So now our universe isn't just full of tiny vibrating strings, it's this whole complex architecture of strings and branes interacting in ways we're still trying to figure out.
So, with all this, strings, extra dimensions, brains, the whole shebang, is this it? Have we finally found it? The theory of everything?
So is this the final answer? The honest answer is that it's really complicated. As beautiful and as promising as string theory is, it also comes with some huge, huge challenges. So let's look at the balance sheet. On the promise side, it gives us a working, mathematically consistent theory of quantum gravity, which is something no other theory has managed to do. It unites all the forces of nature in one package. That's incredible. But then you look at the problems. To actually test it directly, to see the strings, you'd need a particle accelerator basically the size of our galaxy. So yeah, that's not happening anytime soon. And it also predicts a whole zoo of other particles that we've just never, ever seen. But maybe the biggest, weirdest problem of all is this. The theory doesn't predict one universe. The equations have a huge number of possible solutions. And when I say huge, I mean a 1 with 500 zeros after it. It's a number so big it doesn't even have a name. This is called the landscape, and it means there's this vast array of possible universes the theory allows for. So how do we find the one set of rules that describes our universe in that gigantic haystack? We honestly don't know. So you might be asking, okay, if you can't test it and it predicts a gazillion universes, what's the point? And that's a fair question. But history has a way of showing us that the most abstract, seemingly useless ideas can end up changing the world in the most profound ways. I mean, think about quantum physics. 100 years ago, it was the definition of purely theoretical, navel-gazing science, just a bunch of weird equations about a world we could never see. But that useless theory is the reason we have lasers, transistors. It's the foundation of every single computer, every smartphone, the entire digital world we live in. And that kind of leaves us with one last big question to chew on. When people first started playing with electricity, it was seen as nothing more than a fun party trick. Who could have possibly predicted it would lead to, well, everything? The internet, modern medicine, rock and roll? The most profound revolutions often come from the places we least expect. So if we ever do figure out the final theory of everything, where could something like that take us? What could we even do with that kind of knowledge? It's impossible to say, and that's what makes it so exciting.